Let us begin by quieting the mind. Let us drift away from the noise of the daylight, from the screens and the streets, and float outward into the velvet stillness of the night. Imagine, if you will, leaving the atmosphere of our blue world behind. The sounds of Earth fade into a profound silence. The air thins until there is only the vacuum. And here, deep in the cold, expansive dark, 1,000,000 miles away from the home planet, sits a traveler. It is a machine, but it feels like more than that. It is a monument to human curiosity, constructed of beryllium and gold, floating in a precise gravitational dance around the sun. This is the James Webb Space Telescope. It hangs there, suspended in the void at the second Lagrange point, a place of gravitational balance where the pull of the Earth and the pull of the Sun cancel each other out, allowing it to rest in a perpetual silent orbit. It is beautiful to behold. Its primary mirror is a honeycomb of 18 hexagonal segments, gleaming with a layer of gold so thin it is measured in atoms. This gold is not for vanity, it is for reflection. It is designed to catch the faintest, oldest light in the universe, light that has traveled for billions of years, stretching and tiring as it crosses the expanding cosmos, shifting from visible light into the infrared. To see the invisible, one must be cold. Heat is the noise of the universe. Heat is vibration. And so, the telescope protects itself with a sun shield, a 5-layered kite the size of a tennis court, separating the hot side facing the sun and the Earth from the cold side facing the unknown. On the hot side, temperatures can boil water. On the cold side, where the mirrors live, it is deep cryo-freeze, colder than the surface of Pluto. It is here, in this frozen silence, that the golden eye opened. It did not open to see the stars we know. It did not open to look at the moon or the planets of our own solar system, though it can see them with startling clarity. It opened to look back, to look past the spiral arms of the Milky Way, past the neighboring galaxies of Andromeda and Triangulum, past the great clusters of Virgo and Coma. It opened to look at the beginning. There is a concept in cosmology that speaks of the Dark Ages. This is not a metaphor for a lack of knowledge, but a literal description of an epoch in our universe's history. After the Big Bang, after the initial blinding flash of energy cooled and the first atoms of hydrogen and helium formed, the universe went dark. There were no stars, there were no galaxies. There was only a vast drifting fog of neutral hydrogen gas, a sea of darkness that stretched for hundreds of millions of years. The universe was waiting. It was a silent ocean, rippling with the tiniest fluctuations of density, the seeds of what was to come. Gravity, the great sculptor, was working in the dark. Slowly, agonizingly slowly, gravity began to pull the gas together, atom by atom, cloud by cloud. The gas fell inward, swirling, heating up, becoming denser and denser until, in the hearts of these collapsing clouds, nuclear fusion ignited. The first stars were born. The cosmic dawn had arrived. This is the story we have told ourselves for decades. It is a story of a slow, gradual awakening, a story where the universe took its time. We believed that the first galaxies were small, messy, chaotic things, clumps of gas and a few oversized blue stars barely holding themselves together. We believed that it took billions of years for these infant blobs to merge and grow into the majestic spiral structures we see today. We believed that structure emerged from chaos very, very slowly. This was the map we had drawn. We had a timeline. We had a model of how the universe grew up. We called it the Lambda CDM model, the standard model of cosmology. It is a robust, beautiful theory that explains almost everything we see. It tells us how much dark matter there is, how the universe expands, and how galaxies form. But maps are drawn by explorers based on what they can see. And until recently, our vision was limited. We were like people standing on the shore of a foggy ocean, trying to guess what lay on the distant horizon based only on the waves lapping at our feet. The James Webb Space Telescope was built to pierce that fog. It was built to peer into that ancient era, to see the very first lights turning on in the dark. We expected to see the baby photos of the universe. We expected to see the faint, fuzzy, tentative beginnings of galaxies. We expected to confirm what we thought we knew, that the early universe was a simple, quiet place, just waking up from its long slumber. The telescope pointed its golden mirrors at a patch of sky that appeared empty. It opened its shutter. It let the ancient photons, weary from their 13 billion-year journey, strike the detectors. It gathered the light for hours, days. And when the images came back, when the data was processed and the pictures were rendered on the screens of scientists in Baltimore, in London, in Tokyo, the silence of the control rooms was broken not by cheers of confirmation, but by a collective, hushed gasp. The map was wrong. Or, if not wrong, it was missing a massive, impossible continent. Webb had looked into the region where space should have been empty, or at least quiet. It looked into the deep past, less than 500 million years after the Big Bang, a time when the universe should have been in its infancy, a time when galaxies should have been tiny, disorganized sparks in the night. Instead, shining back from the abyss were monsters. There were galaxies. Huge galaxies. Galaxies as bright and massive as our own Milky Way, sitting there in the dawn of time, fully formed, structured, and teeming with stars. They were sitting in a region of space-time that shouldn't have been able to support them. They were like finding a fully grown oak tree in a garden that had been planted only yesterday. This is the mystery we are here to explore. This is the story of the impossible region. A place in time that defies our understanding of how the cosmos works. A discovery that has sent ripples through the scientific community, whispering that perhaps, just perhaps, we have misunderstood something fundamental about the universe. So, let us drift closer. Let us float through the data streams, through the infrared light, and approach these ancient giants. Let us try to understand what it means to find a city in the desert where we expected only sand. This is the journey of the unexpected, the journey into the region space shouldn't have. Part 2, the breaking of the dawn. Let us settle deeper into the narrative of this discovery. Imagine the data arriving. It does not come as a photograph in an envelope, it comes as a stream of numbers, a digital rain falling from the antenna of the Deep Space Network. These numbers are caught by dishes in Australia, California, and Spain, and funneled into the archives. Astronomers, those patient watchers of the night, dive into this stream. They are looking for redshift. In the expanding universe, light stretches. As space itself grows larger, the waves of light traveling through it have pulled apart, like a slinky being stretched out. Light that started as high-energy ultraviolet or visible blue light is stretched, over billions of years, into the red and eventually into the infrared. The farther away an object is, the faster it is moving away from us, and the more its light has been stretched. We call this redshift, denoted by the letter Z's. A redshift of 0 is here, now. A redshift of 1 is far away. A redshift of 7 is the dawn of the universe, less than 1 billion years after the Big Bang. Before James Webb, we had seen hints of things at redshift 8 or 9, faint smudges pushed to the very limit of the Hubble Space Telescope's capability. Hubble was like a mariner straining his eyes against the mist, seeing only the vaguest shapes. Webb was designed to see clearly at redshift 10, 15, perhaps even 20. It was designed to go where the light is so stretched it becomes invisible to the human eye, invisible to Hubble, visible only to the cold gold mirrors of the new observatory. The first images released to the public were dazzling, the Carina Nebula, the Stephens Quintet. But the cosmologists were looking past the beauty. They were looking at the background. They were looking at the tiny red dots scattered behind the foreground stars. They focused on a survey known as SEARS, the Cosmic Evolution Early Release Science Survey. They focused on another called JADES, the JWST Advanced Deep Extragalactic Survey. They began to catalogue the galaxies found in the deep, deep past, and almost immediately the numbers didn't add up. In the standard model of cosmology, galaxy formation is a hierarchical process. It is a bottom-up construction. You start with small clumps of dark matter, the invisible scaffolding of the universe. Gas falls into these small clumps. It cools and makes a few stars. These are the building blocks. Gravity then pulls these small blocks together to merge and form larger blocks. Over billions of years, these mergers continue, building up the spiral and elliptical galaxies we see today. It is a slow process. It takes time for gravity to do its work. It takes time for gas to cool. It takes time for stars to live, die, and enrich the universe with heavier elements. According to our simulations, vast computer programs that model the evolution of the universe from the Big Bang to the present day, the universe at redshift 10, about 450 million years after the Big Bang, should have been sparsely populated. The galaxies there should have been low mass, possessing perhaps 1% of the stars found in the Milky Way. They should have been dim. But when the team analyzed the light from the Webb candidates, they found galaxies like JWST 4. They found galaxies that were massive, not just big for their age, but truly, impossibly massive. Some of these objects appeared to contain as much stellar mass as the Milky Way, but they existed at a time when the universe was only 3% of its current age. Imagine walking into a nursery school and finding a fully grown, grey-bearded philosopher sitting among the toddlers, reading a complex text. It is jarring. It feels like a violation of the natural order. How could nature create so much, so fast? To form a galaxy of that size in such a short window of time requires a rate of star formation that borders on the physical limit. It means that gas must have been turning into stars with almost 100% efficiency. Every atom of hydrogen that fell into the gravity well would need to become part of a star almost instantly. But we know that star formation is usually inefficient. When stars form, they are violent. They heat up the gas around them. They blow stellar winds. When massive stars die, they explode as supernovae, pushing the gas away, blowing it out of the galaxy and stopping the formation of new stars. This feedback loop usually slows down the growth of galaxies. It keeps them in check. The galaxies Webb saw seemed to have no check. They seemed to have converted gas into stars at a breakneck speed, ignoring the feedback, ignoring the rules, growing fat and bright in the cosmic dawn. The region they inhabit, this high redshift epoch, was supposed to be a region of slow, tentative growth. Instead, it is a region of boom, a region of unexpected maturity. The tension this creates in the scientific community is palpable, though it is a quiet, thoughtful tension. Papers are published with titles that contain words like unexpected, challenge, and tension. Theorists are scrambling back to their whiteboards. Are our distance measurements wrong? Could these galaxies be closer than they appear, masquerading as ancient giants? This was the first hope of the skeptics. Perhaps the calibration was off. Perhaps dust was mimicking the signature of high redshift. But as the months went by, the spectroscopic confirmation came in. Spectroscopy is the gold standard of astronomy. It is the fingerprint of light. It breaks the light down into its constituent colors, revealing the chemical elements and the precise stretching of the waves. The spectroscopy confirmed it. These galaxies really are that far away. They really are that old. They really are that bright. So, we are left with the other possibility. The region space shouldn't have is real. The map was wrong. The universe started faster, harder, and brighter than we ever imagined. This realization forces us to reconsider the very nature of the early universe. It forces us to ask what was happening in those first distinct moments. Was the primordial gas different? Was gravity behaving differently? Or is there something else, something hidden in the dark sector, the dark matter and dark energy that accelerated the process? As we drift through these thoughts, visualize the early universe not as a slow awakening, but as a sudden, brilliant fireworks display. Imagine the darkness being punctured not by flickering candles, but by roaring bonfires. The light from these bonfires has traveled for 13 billion years to reach the golden honeycomb of Webb. It has passed through the epoch of reionization, through the web of cosmic filaments, past the great clusters of later eras, finally arriving at the quiet point of L2. And now that we have seen it, we cannot unsee it. The impossible region is on the map. It is a new continent of time, populated by giants. We must now explore the implications. If galaxies grew this fast, what does it mean for the first black holes, for the first planets, for the possibility of life in the very early universe? The discovery changes the texture of the cosmos. It makes the universe feel more fertile, more urgent, more alive from the very beginning. It suggests that the cosmos has a drive toward complexity that is more powerful than our conservative models allowed. We are floating in a universe that is stranger than we knew, a universe that does not wait, a universe that rushes toward the light. In the next part of our journey, we will delve deeper into the mechanisms that might explain this rapid growth. We will look at the role of the seeds of these galaxies, the supermassive black holes that may have anchored them. We will explore the concept of dark stars and the exotic physics that might have ruled the dawn. But for now, let us simply rest in the wonder of the observation. Let us hold the image in our minds, the deep black velvet of the early cosmos, punctuated by the bright, defiant light of galaxies that simply shouldn't be there. They are the ancient ancestors, the unexpected parents of the spiral beauty we inhabit today. They are the mystery that keeps us looking up. The golden eye remains open. The data continues to fall like rain. And with every drop, the ocean of our ignorance recedes just a little, revealing the strange, beautiful shoreline of the true universe. Part 3: The Monsters in the Cradle. To understand why the impossible region is so disturbing to a physicist, we must talk about hunger, specifically the hunger of black holes. Deep in the centers of the galaxies Webb has found, those bright, mature islands in the infant universe, there is often a shadow, a supermassive black hole. These are the anchors of the cosmos, the gravitational drains around which galaxies spin. In our modern universe, we expect them. Sagittarius, AS, the black hole at the center of our own Milky Way, is 4 million times the mass of the Sun. It is a quiet, sleepy giant. But in the early universe, in the region Webb is mapping, we expected these giants to be mere children. We expected seeds, small black holes formed from the death of the very first stars. Here lies the problem. It is a problem of speed. In physics, there is a speed limit for how fast a black hole can grow. It is called the Eddington limit. Imagine a black hole trying to eat a cloud of gas. As the gas falls in, it speeds up, crashes into itself, and heats up. It gets incredibly hot, millions of degrees. This heat creates light. X-rays, ultraviolet rays, a blinding wind of radiation. If the black hole tries to eat too fast, the light it creates becomes so powerful that it pushes the food away. It chokes on its own meal. The radiation blows the gas back out into space before it can cross the event horizon. This limit suggests that black holes should grow slowly, doubling in mass only every few tens of millions of years. But Webb has found monsters that defy this limit. It has found black holes that are millions, sometimes billions of times the mass of the Sun, existing just a few 100 million years after the Big Bang. If you start with a small seed, a single dead star, and feed it as fast as physics allows, you simply cannot get to 1 billion solar masses in the time available. The math does not work. It is like finding a toddler who is 7 feet tall and weighs 300 pounds. You cannot explain it by saying they ate their vegetables. There must be something else happening. This leads us to one of the most compelling and terrifying theories emerging from the Webb data, the heavy seeds. Perhaps these black holes did not begin as stars at all. Perhaps the early universe was so dense, so hot, and so rich in gas that entire clouds weighing 10,000 or 100,000 times the mass of the Sun, did not fragment into stars. Instead, under the crushing weight of gravity, they collapsed directly. They bypassed the star stage entirely. They blinked out of existence and became a black hole instantly. This is the direct collapse scenario. A birth without a star, a shadow born from the gas. If this is true, then the early universe was not just a place of light, it was a place of sudden, massive shadows appearing in the dark. These heavy seeds would have given the universe a head start. They would have started the race not at the starting line, but halfway to the finish. Webb has seen hints of this. It has found a class of objects astronomers are calling little red dots. To the untrained eye, they look like faint red smudges, but when we analyze their light, we see something extraordinary. They are tiny, compact, much smaller than a galaxy should be, but they are shining with the intensity of a quasar. They are likely these heavy seeds, wrapped in cocoons of dust, eating voraciously, breaking the Eddington limit, ignoring the rules of the modern universe because the rules of the infant universe were different. We are looking at a time when the cosmos was wilder, a time when monsters were born in the cradle. And these monsters may be the reason the galaxies around them grew so fast. Perhaps the black hole didn't form inside the galaxy. Perhaps the galaxy formed around the black hole, drawn in by its immense gravity, like moths to a dark flame. Part 4. The Ghosts of Dark Matter. As we ponder the heavy seeds, another possibility rises from the theoretical mist. A possibility that is even stranger, even more ghostly. We know that the universe is made mostly of stuff we cannot see. Dark matter. It makes up about 85% of the matter in the cosmos. It does not reflect light, it does not block light. It only interacts through gravity. It is the invisible scaffold that holds galaxies together. Without dark matter, the Milky Way would fly apart. In the modern universe, dark matter is spread out. It is a diffuse halo. But in the beginning, in the first epoch, the universe was smaller. The dark matter was denser. There is a theory, resurrected and energized by the Webb discoveries, that suggests the first stars were not powered by nuclear fusion at all. When we look at the Sun, we are seeing a nuclear reactor, hydrogen crushing into helium. But what if the first stars were made of hydrogen, but powered by the darkness? They are called dark stars. The name is misleading. They would not be dark, they would be the brightest things in the universe. Here is the idea. In the centers of the first protogalaxies, dark matter was so concentrated that the dark matter particles, WIMPs as they are sometimes called, began to collide with each other. And when matter and antimatter collide, they annihilate. They turn into pure energy. If a cloud of hydrogen gas began to collapse in a region thick with dark matter, this annihilation energy would heat the gas up. It would heat it up so much that the cloud would stop collapsing. It would never get dense enough to ignite nuclear fusion. It would just sit there, a giant, puffy cloud of hydrogen, glowing with the heat of the dark matter burning inside it. These dark stars would be titanic. A single dark star could be 1,000,000 times the mass of the Sun. It would not be a solid ball of plasma like our Sun, it would be a diffuse ghost, a star so large that if you placed it in our solar system, it would swallow everything out to the orbit of Saturn. And because they are so cool in terms of temperature and so massive, they would shine with a brilliant infrared light. This is the chilling possibility some of the galaxies James Webb has identified might not be galaxies. When we look at a smudge of light from the dawn of time and we say, that is a galaxy with 100 million stars, we might be wrong. It might be one single object, one single dark star masquerading as a galaxy. This would solve the impossible problem instantly. We don't need to explain how a galaxy formed so fast because it isn't a galaxy, it's a star that can grow incredibly quickly, fed by the dark matter around it. Webb has found candidates. There are objects, JADs, GS, 713, 730, 730. They are incredibly bright. Their light signature matches the theoretical prediction of a dark star better than it matches a standard galaxy. If this is true, it changes everything. It means that the first epoch of the universe was not the era of stars as we know them. It was the era of the dark giants. And what happens when a dark star dies? when the dark matter fuel runs out. The gravity takes over. The giant, puffy cloud, 1,000,000 times the mass of the Sun, collapses. It does not go supernova. It is too big for that. It simply falls inward. The entire million solar mass object vanishes into a single point. It becomes a supermassive black hole. It becomes the heavy seed. Do you see how the pieces might fit? The dark stars could be the parents of the monsters. They explain the brightness we see, and their death explains the black holes we find later. It is a beautiful, elegant, and haunting narrative. It suggests that the dark matter we search for in our underground laboratories without success was the dominant force of light in the beginning. It suggests that we are the children of the ashes of these dark giants. As we drift away from this idea, let us remember that this is still a hypothesis. But it is a hypothesis that has moved from the chalkboard to the data stream. The universe is forcing us to dream bigger. It is showing us that in the deep past, the line between a star, a galaxy, and a black hole was blurred. We are looking at a time of transformation, a time when the physics of the universe was raw, violent, and incredibly creative. In the next chapter of our journey, we will move forward in time. We will watch these first chaotic structures, whether they were galaxies or dark stars, begin to merge. We will witness the violent assembly of the cosmic web. We will see how the impossible region settled down into the structured spiral beauty we know today. We will explore the cosmic noon, the peak of star formation, and see how the chaos of the dawn gave way to the order of the day. But for now, let the idea of the dark star linger, a single light, lonely in the void, burning with the energy of the invisible. A ghost lantern lighting the way for the galaxies to come. Part 5. The Architecture of Light. Let us move forward now. Let us leave the impossible region of the deep dawn, that era of monsters and dark stars, and drift toward the present. We do not jump instantly to today. We stop in the middle. We stop at an era known as cosmic noon. This is a time, roughly 3 billion years after the Big Bang, when the universe was in its teenage years. It was a time of peak activity. The heavy seeds had grown into supermassive black holes. The dark stars, if they existed, had collapsed. The first chaotic blobs of gas had begun to merge. James Webb has shown us that the transition from the chaotic, impossible, early universe to this structured era was violent and beautiful. It was a time of construction. Imagine a construction site on a galactic scale. Streams of cold gas, rivers of hydrogen flowed along the invisible filaments of the cosmic web. They poured into the centers of galaxies, feeding the black holes and fueling the birth of new stars. In the impossible region, star formation was a sprint. In cosmic noon, it was a marathon run at a sprinter's pace. Galaxies were colliding. When two spiral galaxies crash, it is a slow-motion dance that takes hundreds of millions of years. They pass through each other. Their stars rarely collide because space is so vast. But the gas clouds. The gas clouds smash together. Webb allows us to see this dust. Invisible light, dust is a nuisance. It blocks the view, it hides the stars. But in the infrared, the dust glows. It shines with the heat of the stars born inside it. Webb has revealed that the impossible galaxies of the dawn were surprisingly rich in heavy elements. Carbon, oxygen, nitrogen. These are the ashes of dead stars. For a long time, we thought the early universe was pristine, just hydrogen and helium. We thought it took billions of years to build up the stuff of life. But the data from Webb suggests that the universe got to work on chemistry very quickly. The impossible speed of galaxy formation also meant an impossible speed of chemical enrichment. The universe was polluting itself with life-giving elements far earlier than we dared to dream. This changes our perspective on our own origins. We used to think that the ingredients for planets and life were latecomers to the cosmic party. We thought Earth-like planets couldn't exist in the early universe because there wasn't enough rock, enough iron, enough silicon. But if the impossible region is real, If galaxies matured that fast, then the periodic table filled up fast too. Rocky planets might have formed around stars that lived and died 10 billion years ago. There may have been worlds of stone and water floating in the dark long before the Earth was even a concept in the mind of gravity. We are drifting through a universe that feels lived in. It feels older, in a way. Not in years, but in experience. Webb shows us the PAHs, polycyclic aromatic hydrocarbons. These are complex organic molecules. They are the soot of the universe, but they are also the building blocks of prebiotic chemistry. We see their spectral fingerprints glowing in galaxies that existed when the universe was a fraction of its current age. The architecture of light we see today, the grand spirals, the elliptical giants, was built on the foundation of that early, frantic acceleration. The region space shouldn't have was the kiln. It was the forge. It was the place where the universe rushed to get the difficult work done so it could settle down into the long, stable burn that supports life today. As we look at these images, at the intricate spider webs of dust in the phantom galaxy, or the pillars of creation seen through the penetrating gaze of the near-infrared camera, we are seeing the aftermath of that early rush. We are seeing the smoke clearing after the fireworks. The universe we live in now is the legacy of those monsters. We are here because they were there. We are made of the heavy elements they forged in their impossible furnaces. Part 6. The Map Maker's Silence. And so, we return to the beginning. We return to the silence of the second Lagrange point. We return to the golden machine floating in the eternal night, its sun shield facing the fire, its mirrors facing the ice. We started this journey with a title, James Webb, Just Mapped a Region Space Shouldn't Have. It sounds alarming, it sounds like a mistake, but in science, a mistake is often just the universe whispering a deeper truth. The map has changed, the timeline has shifted. The empty spaces on the chart have been filled with giants. We have learned that the dark ages were not so dark. We have learned that the dawn was brighter, faster, and more violent than we imagined. We have stared into the face of heavy seeds and dark stars. We have seen the universe waking up not with a yawn but with a roar. What does this mean for us, the observers? It reminds us of our scale. We are small, fleeting consciousnesses on a small, wet rock, orbiting an average star in the suburbs of a spiral galaxy. And yet, we built a machine that can see the beginning of time. We built a machine that can catch a photon that has been traveling for 13.6 billion years and turn it into an image on a screen. The impossible region is only impossible because our imagination was too small. The universe is not limited by our models. It is not limited by our simulations. It is wilder than our math. There is a profound comfort in this. If we knew everything, if the map was complete and accurate, the journey would be over. But the map is never finished. Every time we build a better ship, we find a new ocean. The James Webb Space Telescope has years of life left. It has fuel to keep its station. It has cooling fluid to keep its instruments frozen. It will continue to stare into the deep fields. It will find more monsters. It will find more impossibilities. And with every discovery, the silence of the cosmos becomes a little less empty. It becomes filled with a history that belongs to us. As you drift off to sleep, or as you return to the world of the daylight, carry this image with you. The universe is not a stagnant place. It is a place of frantic, creative energy. It is a place that wanted to be. It hurried to create the stars. It rushed to create the carbon in your cells. The region space shouldn't have is the region that made us possible. The golden eye closes its shutter for a moment, calibrating, preparing for the next exposure. The data flows. The knowledge grows. And we, the children of the stardust, continue to watch, continue to wonder, and continue to map the infinite dark. Part 7. The Alchemy of the Void. As we linger in the afterglow of the impossible dawn, we must ask a fundamental question. Where did the stuff of us come from? If the early universe was a place of frantic, hyper-efficient star formation, it was also a massive chemical factory. We mentioned earlier that Webb found heavy elements, carbon, oxygen, nitrogen, much earlier than expected. This is not just a footnote in a dusty textbook. This is the origin story of your blood, your bones, and the air you breathe. Let us drift away from the edge of time, back toward our own galaxy, but keep the lesson of the impossible region in mind. Because those ancient monsters, those hyperactive galaxies, were the gardeners of the cosmos. They seeded the void. When a massive star dies, it does not just fade away. It detonates. It takes the atoms it fused during its life, the carbon created in its core, the iron built up in its final moments, and it blasts them out into the empty space between the stars. Because the early universe was so much more active than we thought, this enrichment happened fast. The void was not empty for long. It was filled with the dust of diamonds, the soot of carbon, the ice of water. James Webb has turned its golden eye toward this dust in our own neighborhood. It has looked at the Orion Bar, a ridge of gas in the Orion Nebula. There, it sees the same process happening today that happened 13 billion years ago. It sees starlight hitting carbon molecules, making them vibrate, making them glow. But Webb does something else. It looks for this dust where it matters most, around other stars, around exoplanets. If the universe grew up fast, if it created the ingredients for life in the first few 100 million years, then the potential for life is not a modern phenomenon, it is an ancient one. Webb is currently staring at the TRAPPIST-1 system, 7 rocky worlds orbiting a red dwarf star. It is looking for atmospheres. It is looking for the spectral signature of water, of methane, of carbon dioxide. It is looking for the alchemy that turns rock and gas into a living world. The discovery of the impossible region gives us hope for these worlds. If galaxies could mature quickly, perhaps planets could too. Perhaps the stability needed for life doesn't require 10 billion years. Perhaps life is a weed that grows as soon as the ground is ready. Imagine standing on the surface of a planet in the early universe. The sky would not be black. It would be ablaze with the light of star clusters forming nearby. The night would be bright with the glow of the active galactic nucleus, the supermassive black hole feeding in the center. It would be a dangerous, violent sky. But chemically, the water in your glass would be the same as the water on Earth. The carbon in the soil would be the same. The impossible region tells us that the universe was ready for us, chemically speaking, a long, long time ago. We are late arrivals to a house that was built in a hurry. This realization shifts our loneliness. We often feel that we are a fluke, a lucky accident that happened after billions of years of rolling the dice. But the data suggests the dice were loaded. The universe was trying to make complex things from the very start. The drive toward complexity, toward heavy elements, toward chemistry, was baked into the initial conditions of the Big Bang. So, when we look at the impossible galaxies, we are not just looking at anomalies, we are looking at our ancestors. We are looking at the great-grandparents of the periodic table. We are seeing the moment when the universe decided it would not be just gas, but dust. And from dust, eventually, comes the dreamer. Part 8. The Eternal Question. Let us take a moment to reflect on the nature of impossible. Throughout history, humans have drawn maps. We drew maps of the land, and where the land ended, we drew sea monsters. We wrote, "Here there be dragons," the impossible region. James Webb has mapped is the modern equivalent of those dragons. It is the place where our knowledge runs out and the mystery begins. But in science, dragons are not to be feared. They are to be hunted. The tension in cosmology. The disagreement between the early universe we see and the standard model we built is the most exciting thing that has happened in physics in decades. A perfect agreement is boring. It means we have nothing left to learn. A disagreement, a contradiction. That is a crack in the wall. And through that crack, the light of a new physics might be shining. Perhaps our understanding of gravity is incomplete. Perhaps the laws of physics themselves evolve over time. Perhaps the speed of light, or the strength of the gravitational constant, was slightly different in the dawn of time. These are the whispers now circulating in the quiet corridors of theoretical physics departments. The impossible region is forcing us to be humble. It is reminding us that the map is not the territory. James Webb is a time machine, but it is also a mirror. It reflects our own limitations. We built a machine to confirm our theories, and the machine politely, gently told us we were wrong. There is a beauty in being wrong. It means the universe is still capable of surprising us. As we continue to download the data, as the years of the mission stretch out, we will see deeper. We will look for population 3 stars, the very first generation of stars made of pure hydrogen with no heavy elements at all. We haven't found them yet. Maybe they are hiding behind the impossible monsters. Maybe they lived and died so fast that they are gone forever, leaving only their chemical ghosts. And beyond the stars, Webb looks at the dark ages themselves. It tries to see the neutral hydrogen fog before the lights turned on. It tries to see the moment of ignition. We are floating in a cosmos that is vast, dark, and mostly cold. But it is punctured by these islands of furious light. And on one of those islands, orbiting a yellow star, a species of bipedal apes has figured out how to polish beryllium until it is smoother than a virus, coat it in gold, and fling it 1,000,000 miles away just to catch a glimpse of where they came from. That act, the act of looking, is as significant as the galaxies themselves. The universe creates the stars, but it takes a mind to appreciate them. It takes a consciousness to be awed by the impossible. So, as we end this extended chapter of our journey, do not feel small, feel connected. You are made of the heavy elements forged in the impossible dawn. You are the universe looking back at itself, trying to understand the frantic, beautiful, impossible hurry it was in to create you. The telescope drifts on. The sunshield holds back the heat. The mirrors catch the ancient photons. And the map grows larger, more detailed, and more mysterious with every passing hour. We are just beginning to see.